Hello everyone. In this video, we are going to talk about one of the complicated topics in robotics that is called Simultaneous Localization and Mapping, or SLAM. As with other videos that I recently published, the material is mostly taken from Introduction to Autonomous Mobile by Sigwart, Nurbakhsh, and Scaramuza. So what is a SLAM and why do we need it and why is it very hard? So in the past, we have seen that if you want to localize yourself, you can use basically odometry, right? You can use the encoders and approximately find yourself and how much you moved, but it is subjected to drift. It has uncertainty that grows as you move on. That's actually my previous video if you watched it. So you cannot just rely on encoders to localize yourself perfectly, and you need some extra things, typically from the environment, to localize yourself more accurately. Like what? Like, for instance, if you are operating outdoors, many robotic agents are using GPS, right? Like drones and airplanes and so many other things, autonomous ones. And if you don't have access to them, then indoors you might use some landmarks of the environment, right? So you can use those. Good. On the other hand, sometimes you want to create a map of the environment. The environment is unknown, you don't have a map of it, and you have to create a map. So your localization should be relatively accurate, and then when you are at any position, you can use your range sensors and cameras and create a map of the environment. By the way, one of my upcoming videos, I use a LiDAR on a Scara robot, and I show you how to create a very, very rough map of the surrounding of the robot, because the LiDAR is going to be a 2D LiDAR. Now, if you want to localize yourself using the landmarks of the environment, then you need to know the environment very well. In other words, your map has to be accurate. Let's say, for instance, here, look at this robot. This robot is seeing two landmarks, M1 and M2. And if the location of this M1 and M2 is perfectly known, then by, let's say, having a camera that is looking at the scene, it knows the location of these two landmarks, and it can get the bearing angle for M1 and it can get the bearing angle for M2, and by a triangulation, the robot can localize itself very accurately. On the other hand, if I know the location of the robot very well, so I know this robot is right here perfectly, then if I can use a LiDAR here, right, a scanning LiDAR, and I scan this object, different basically radial distances and angles, then I can go around this object and I can find all of the boundaries of it, okay? But I have to go probably around it at different positions. And if I want to get a good map, my localization has to be very accurate. But if you want to do both of them at the same time, so you don't have accurate localization, you don't have accurate map, or none at all, no map at all, you have to do both of them at the same time. But the thing is, these two, as I just explained, are kind of correlated to each other. They are entangled. The accuracy of one will affect the accuracy of the other one, and if they're both inaccurate or one is non-existent, like a map, then that is going to make this problem very hard. That is going to be like a chicken and egg problem. Okay, so we want to look into this problem, and first thing is, why should we do that, right? Can't we just do one of them? The answer is no, not always the doing localization or mapping individually is possible. So when do we need the SLAM? One is when you're operating in an unknown environment, like when you send the Mars rover. This Mars rover does not have a floor plan or a topography plan of the Mars very accurately. We don't have satellites going around the Mars too many, as far as I know. And there are no roads or buildings or anything. So that vast landscape of Mars without too many landmarks is not really easy to localize yourself. If you're sending something to go and explore it, the environment, create a map, and then maybe coming back. Okay, so in unknown environments, or if you remember the Fukushima nuclear reactor in Japan, after tsunami, it melted down and it has a collapse and a disaster. They sent some robots inside the building to get an idea of the extent of damage. Well, you might say, I know the floor plan of that Fukushima building. Yes, you know it before everything collapsed. When the building collapsed, some of those doors, walls, windows, stuff like that are not there anymore. There are lots of rubble on the road and so on. So it's not the same floor plan that you used to know. So if you are navigating unknown environments, you don't have a map, okay? Or your map is not accurate. Or sometimes the environment is dynamic. You had something, but they moved it significantly and you have to remap it. Like consider the Roomba robots that are cleaning your houses, right? For those robots, clearly the environment of the house is not perfectly static. You move furnitures around sometime and they have to recreate the map of the environment and at the same time localize themselves so they can come back to their charging station. So SLAM is a serious task for many applications. And the other thing is, as I said, if you want to localize yourself without drift, you cannot just rely on your what we call let me show you the word that is a technical word so you know it, is called the proprioceptive, or the sensors that are only measuring from inside the robot with no interaction with the environment. You cannot just rely on them like encoders. You need the exteroceptive ones that are interacting with the environment, like camera, like LiDAR. They could be active or passive, but you still need them. And sometimes these sensors are not available, like GPS, like Wi-Fi, like pre-placed markers. They are not always available. Not every environment has markers you can easily identify. Not every place has a Wi-Fi or beacon. And in many indoor environments or dense urban canyons or underground, GPS is not available. So you have to, and their maps might not be super accurate as well. That's where you need to do SLAM. Okay. So I'll come back to this loop closure in a second, but let's see what is the mathematical definition of SLAM. So what is it? Here, we're gonna focus on a 2D robot, and it could be differential drive or anything. But if we have a 2D robot, as you know, the pose of the robot has 3 parameters, x, y, and theta. Okay? So if you define the pose of the robot at any time point by variable x of t, which has these 3 variables in it, and this x is a vector, and if you accumulate these x's of t, x of 1, x of 2, all the way to x of t, where this t is the end point of the path of the robot, and that t could be finite or infinite, then these x's would represent the robot path. Okay, so a bunch of points on the robot path, basically, right? These points on the robot path, these form the x of t. Okay, all of the poses of the robot at different waypoints on the path. One other thing we have to say is the initial position of the robot has to be known relatively well, but the other ones not. So this x of 1, we typically know it very well, but this x2 all the way to xt, we don't know, okay, very well, okay? Because let's say we are only using encoders, and the goal is to, we'll see, is to retrieve them. The things that we know well are the command motions that you give to the robots. And it could be the velocities of the 2 wheels. It could be V and omega if you're looking at kinematics. If you're looking at kinetics, it could be the torque that you pass to the left and the right tire if it's a differential drive or something. Okay, so the motion command of the robot at any time point, u of t, is also well known. You know how we commanded the robot Also, the observation of the sensor of the robot or sensors of the robot Z of t, which you take from the environment landmarks at any time point. It could be from LiDAR, from camera, anything. This is also known. You have a sensor and you can make a measurement or observation along the path. So this matrix that is with all of these motion inputs, and this matrix, which is all of the observations, these two are fully known. Z of t and U of t are known. X of t is typically unknown, except for the first one. And the other thing that you don't know is the map of the environment. So here we put all of the landmarks of the environment in a matrix. So if we can represent each landmark by a vector, like M0, M1, all the way to Mn-1, right? So you see the number of landmarks is different from the number of the waypoints, okay? The number of waypoints is T, capital T, but here the number of landmarks is N. So, and these landmarks could be lines, points, planes, or any high-level features like doors, windows, or anything. This M is also unknown. The map of the environment is something we don't know. So the definition of a SLAM is to find the joint probability of map and the pose of the robot at all points, given the observations and the motion commands. Okay, this is the definition of SLAM. Now here, when we say SLAM, there are two definitions that we need to know. One is called the full SLAM, the other one is called online SLAM. What is the difference? In full SLAM, you need to recover all the history of the motion, all of the points from the first point all the way to the last waypoint. In online SLAM, you're only considered about the current position and the map, not previous points. So you care about the current pose in online, but in full, you want all of the path history. Okay, so of course, the full SLAM needs more computation than online SLAM does. But if somebody says, what is the difference between online SLAM and full SLAM, at least here, you know that. So, how is this problem solved? There are three major categories of solutions to the SLAM. As far as I search, there is always a chance of a new one appearing. But the three major categories are EKF-SLAM, the original and the first one that is used a lot, which is based on extended Kalman filter. The other one is graph-based SLAM, and there is another one, particle filter SLAM. Now, if you don't know EKF, what EKF is, or if you don't know what is particle filter, I recommend you watch the relevant videos on my channel under playlist controls. Let me show you. So this is one of them, extended Kalman filter, or EKF. Okay, and extended Kalman filter is the version of Kalman filter which is used for nonlinear systems, because in our robots, our motion model and our observation models are both nonlinear, so we have to use extended Kalman filter. But if you don't know what Kalman filter is in the first place, I recommend you first watch Kalman filter, then go to extended Kalman filter. I also have videos about unscented Kalman filter if you're interested, and then I should have a video about particle filter. Okay, so if you want to know about particle filter or sequential Monte Carlo, I also recommend you watch this video so you have an idea of what I'm talking about in this video. Okay, so the one that I'm going to look in this video is the original one, extended Kalman filter SLAM. So we're going to work based on that in this video. Okay, and the problem we are going to solve is going to be online SLAM. I mean, you can always, once you solve online SLAM, you can also go for full SLAM. So, but here we are going to look at the least complicated one, which is EKF and online. Okay, and if I have future videos, then I'll mention a little bit about the full SLAM. What would you do? But in general, they need a video of their own. So what do? The first thing we do, we create an extended state vector. Sometimes instead of extended, some people call it augmented. Okay, so the first thing we do, we put all of the unknowns of the problem in one vector, and we call it, let's say, whatever, y of t. And again, this y is a vector. It's different from the y of pose. If you don't like it, call it anything else. So you see the unknown x of t, the current pose, as well as all the landmarks that I don't know, I put them in this vector. The goal is to find this. Good. Now, for instance, in the problem that I'm going to show you a simulation today for, let's say the problem is a 2D problem, and you have n landmarks in the environment, and these landmarks in this case are lines, okay? And as you know, a line has two parameters. If you want to represent a line, you can show it by two parameters. It could be the slope and the y-intercept, but many times, as you know, in computer vision and so on, like if you watched my Hoff transform video, you know that the way they show a line is by a radial distance and an angle, right? So if you have this coordinate frame and this is the line, then they draw the normal from origin to the line, okay? And this radial distance, they call it r, and this angle, they call it alpha. You can also represent any line by r and alpha. So each one of the lines has one r, one alpha. So if you have n lines, you're going to have two n parameters, n r's and n alphas. And your robot pose x of t, remember it has x, y, and theta. So in general, you have 3 plus 2n unknown parameters to find. The first 3, x, y, and theta at time t for the pose. And for each one of the lines, as I said, a pair of alpha and r. Okay, so in general, you have to estimate 3 plus 2n parameters, and you have to do it in a probabilistic framework, because we are dealing with extended Kalman filter, and of course, the problem is probabilistic. Why is it probabilistic? Because our motion model and our observations are nonlinear, but not just nonlinear. It's not the reason is they're nonlinear, because they have randomness to them. So if we go back and look at the EKF, in EKF, we assume that our state transition model comes from a nonlinear function f, and there is some disturbance or randomness in the model. In our case, it is coming from the slipping under the wheels, misalignments, different radii, and anything that we learned in the past that creates uncertainty in odometry. Okay, that's mostly because of that, but there are more things. And then this is our observation model. The observation is a function of the state plus some measurement noise. And of course, you know, when you use a LiDAR or when you use a camera, there are all sorts of noises, right? So, for instance, there is the effect of the environment, right? There is improper reflection of the laser back to this device. There is interference from different lasers. There is, for instance, in the images, there are all sorts of noises and so on, okay? There is one of the biggest things that we'll see later is the improper or wrong association of features and landmarks. That is one of the hardest things. So nothing is done perfectly. Everything is done only with so much probability of being accurate. And in this case, we assume that both this disturbance and the measurement noise are coming from normal distributions with average of 0 and some covariance matrix Q and R. So another thing that we have to set up is Q and R. We have to figure them out and initially start them, okay? And that is another thing that is important, and it will affect the result, as I'll show you in the simulation. And then, as you know, in Kalman filter or extended Kalman filter, there are two steps. One, from the previous state and the previous input of the motion, you predict the current position, which is basically, this is your motion model. As I said, in our case, this is your motion model. or odometry equations. And this is your sensor model or observation model. So first you predict where your state is going to be, and once the prediction is done, then at that prediction, because you have a prediction and you have a function for observation, you basically expect some observation to happen, but the fact is that observation that you get from the sensor is different from the observation that you expect to have. So the difference between actual observation and the expected observation is going to create an error term, which we call the innovation, if you remember. And then we use this innovation term to basically, in the next step that is called the correction, we are going to correct the x that I got from the previous state in the prediction. I add some term to it, again times this innovation, and this is going to be the final or corrected state that I have out of the system. And this k, if you remember, this is called the Kalman gain, right? And the Kalman gain, the formula for it is this, right? And in these two states of prediction and correction, not only you update the state, for each one you also update their covariance matrix, because each one comes with so much uncertainty. So P, the covariance matrix for state X, is updated first during the prediction stage. It is updated. In this update, you see Q, the disturbance noise, right? Disturbance, basically probability, comes into play. So clearly bigger Q will affect this prediction. And this F here, because this P is the previous covariance, this F here is basically the Jacobian of your motion model with respect to the state. And also in the correction, your covariance matrix gets updated one more time, this time by I minus K H of K, where K is that Kalman gain that you have to find from this equation, and H here is the Jacobian of the observation model with respect to the state. Okay? So this is basically the total thing we do. Now in these equations, instead of this X hat, what we'll use is this augmented one. So that augmented state is going to come and replace my X hat and X in these equations, and that is the thing that gets updated. Okay? So this is the essence of the solution. Now, one thing we have to pay attention to is, we said that the number of unknowns, or the ones that we need to estimate, is 3 plus 2n. Now, you know that if the number of lines or landmarks, in this case in the environment, is big, guess what? This 2n is going to be a big number. Let's say we have 1,000 lines in the environment. Then we are looking at 2,003 unknowns, and that means a lot of computations. So that's why in this basic method for EKF, what they do is they try to limit the number of landmarks in the environment, typically to less than 1,000, to keep it manageable in terms of computation, or they divide the entire map, which is defined by these landmarks, they divide it into submaps. So if you have 10,000 lines, they break the map into 10 regions, each one maybe with 1,000 lines, and they create these submaps, and then they merge them. Otherwise, it is not going to be manageable, okay? Because you're dealing with tons of unknowns and their probability estimations. Now, first thing is, here one of the big things we assume is we assume the environment is static. So look at the assumptions we have so far. One, we assume that we know the first position, the first pose. Second is we assume the environment does not change. What does it mean? It means the landmarks, the lines, those M's that we had, they are not going to change. They are going to stay in the same place with respect to the world coordinate. Therefore, when we want to update our state, guess what? The only three states that will get update are the X, Y, and theta. Okay? The M's, they will not get any update because, as I said, in the world coordinate, they should not get updated. Okay? And that makes our computation a little bit simpler because nothing is dynamic. The environment does not change. Okay? So this is in those basically prediction step that you don't need, or in the correction, you don't need to change the M's. You just need to estimate them. Now, so what about the covariance matrix? What happens to the covariance matrix? Well, the thing is this. First thing is, because these are recursive equations, as you can see, you have to start this P at time t0. You have to start it with something, correct? And you have to start X at time 0 as well. But X at time 0, as we said, we know it. So this is good. What about this covariance? How would you start it at time 0? Okay, that's one thing. So at the beginning, what you do is the way you start it. So let's say here, for instance, you have what? Let's say you have one line, just to make it simple. Then your covariance matrix is going to be 5 by 5, correct? Because you have two parameters for the line, alpha and r, and you have x, y, and theta. So it's going to be a 5 by 5 matrix. So for this 3 by 3 portion and for this 2 by 2 portion, this 2 by 2 is for the map part. This 3 by 3 is for this x, y, theta. And these are the off-diagonal components, by the way, which shows the correlation between these x, y, theta, and r and alpha. As you know, they are correlated. The uncertainty of each one will affect the other one. But when you want to start this P0, how do you start it? Because I know my initial position very well, x0, y0, and theta 0, because I know them very well, what you do, you start them with very small numbers and you start them diagonally. So you start with some very small number, very small number, very small number, right? So I don't know, I just show them by, for instance, 10 to the negative 3, 10 to the negative 3, and maybe 10 to the negative 3 or 4. Of course, pay attention that these are in units of meters or millimeters. This is in units of radians. So their scale does not need to be the same, okay? And then elsewhere 0. So initially, you know your position very well. What about the maps? Do you know the map very well? Of course not. Remember, here we assume we don't know anything about the maps. So exactly opposite of that, your diagonal parts, the sub-diagonal part for the map has to start very big. So here you might go with something like 10 to the 6. Okay? Because I don't know anything about the map. The goal is for that to shrink very fast and go to 0 as we scan around the landmark and estimate R and alpha properly. And what do you start these diagonals with, the off diagonals? Initially, we start them with 0. Initially, we start them with 0, okay? Initially, because we assume that no correlation has happened yet. Then what happens as your algorithm starts going around, your robot starts going around and scanning and getting data from the landmarks, making these observation Z's, and your F is evaluated, your H is evaluated, and so on. what would you do over time? What happens to P0 in these prediction and correction stages is, what happens is, as you move away from your initial point, these guys are going to go up because they are only controlled by encoders, and encoders will have drift. So these guys start to go up. On the other hand, the landmarks, as you start getting more data from them, they should start going down on one side because you make observations. On the other side, they also might go up as well because the uncertainty of the position or localization will affect these maps as well. But instead of showing that up here, what you can do is, or what is actually done, because that portion is coming from the effect of these localization parts, what you will do and what will happen is, in these off diagonals, they start to go up because they show the correlation between location and the map. So they start becoming non-zero, okay? And the more you move, the bigger these off diagonals become, the more the position and the map become entangled to each other, which is always a good sign. The bigger they become means your SLAM is doing a better job, okay? And these maps, their covariance should drop down, so you should know your environment better. Initially, as I said, your localization goes up and goes bad, but after some time, it starts going down again. When does it start going down? It typically starts going down when you revisit a place that you have seen earlier, okay? If you have seen a place that you have seen earlier, now that you see it again and you make another observation of that, it's like basically acts something like a GPS for you, right? Because you say, well, let's see. Initially, I was here, okay? And this was my landmark. I moved on this path. I ended up here. I don't know if I'm there. I have an uncertainty ellipse around me because the propagation of uncertainty in position started growing. Now that I'm there, I see some new landmarks and I make some observation of these. And then I come back from here back to, let's say, this position. Of course, my uncertainty grow even further because I'm using encoders, so the uncertainty has increased. But now I can see this guy again. Initially, I saw it. Now I can see it again. And what's the good thing about it? Well, this is the good thing. If my map was good, if this map, the localization, if this localization was good and I'm here really, if I'm here in this red position, because initially I made an observation of this object and initially I know myself very well, so this measurement that I made from this observation, the location of this M naught should be relatively good as well. It should not be really with big covariance. Now that I know where I am, assuming that I know where I am, based on that and based on these locations of this landmark that I initially captured, now I should expect to, let's say, for instance, see this kind of distance from that. Okay, let me clean this up. Now I should expect to see this distance from the landmark. Do I see that? If I do, I know my localization and my path was good. But guess what? When I look at it, I see that, well, the distance I see is actually this much. Because the distance I see is this much, not the green one, the blue one, which is longer, I know I should not be in this location. I should be further away from the map and I have some bearing angle. Then instead of wondering where I am in this big ellipse, I know, guess what? I should be here because of the bearing angle and the distance that my sensor is reporting to me from M0. I would limit that big ellipse to a smaller ellipse. I say, well, I'm inside this smaller ellipse because my sensor is telling me. That's what make your localization uncertainty to shrink. Okay? And this phenomenon is called the loop closure, because you go around the loop, you come back, you revisit the same landmark, and you limit that big ellipse that you had around you to a smaller one because you are making another measurement of a known position, of a known landmark, and this is going to help your localization uncertainty to go down. Okay, so that is called the loop closure, and we're going to see that in the simulation. So over time, if I want to summarize it very fast, the off diagonals, which shows correlation between map and localization, they start to grow. The bigger they are, the better the SLAM. And the maps get better and better. The position first start to grow until a loop closure happens, then they start to go down. And typically when they do SLAM, they do several rounds. Okay, so they typically don't do one round, one loop around the environment. They let the robot really explore and go all over the place. That will help the maps and the localization to get better and better. Okay, because now you're going to have several loop closures and your covariances will drop to small numbers. So this was all about online SLAM. Your goal was to estimate the current pose at any time. What if you want to go back and revisit all of the path, right? Because guess what? If I come back to this picture and I want to explain it, here, your path, if it has to be corrected, if you go from this ellipse to this one, all of these previous ellipses that you had along the way, all of these other ones, they have to also shrink down accordingly. I mean, if I thought I'm here, but now I'm actually here, this shrink down to that, all of these previous ones probably have to shrink to something as well. Okay, so this fixing that you did after loop closure, it has to go back and retroactively affect all of these previous ones, right? And this is the full SLAM problem. Now, how would you do full SLAM? If you watched, I have a video that is called bundle adjustment. I absolutely recommend that you watch this video and also the video for structure from motion, because I'm going to refer to it in a minute for visual SLAM. So these two are very important. And bundle adjustment is about, I fix my current basically pose, and then retroactively I go back to the previous uncertainties and try to shrink them down. And this is an optimization problem that you have to do. It's a costly optimization problem. And that is exactly what you do if you want to go from online SLAM to full SLAM. When loop closure happens, you have to do a bundle adjustment, similar to structure from motion. Okay, so it needs a lot of explanation and so on, but if you watch that video, you exactly know what I'm talking about. So if you want to do full SLAM after online SLAM, you have to do a bundle adjustment. Okay, so far we have assumed that when we basically go after a landmark, we can find two pieces of information for it: the bearing angle and the range. Okay? So the thing is, many times we might not have or prefer not to use a sensor that gives us both of them. Sometimes we only use a camera, and as you know, camera only gives you a bearing angle and no range. If you use LiDAR, it gives us both, or ultrasonic, but if you use a camera, we only have the bearing angle. So basically, we cannot fully measure our landmarks. Instead of R and alpha, you can only get alpha. So if you use a camera, we call it V-SLAM or visual SLAM. That's when you do SLAM with a camera instead of a LiDAR. And one of the cases is you do a single camera, that is the hardest case. We call it monocular VSLAM, because you absolutely would lose the range. Now you might say, is there a case that you don't lose the range with cameras? Yes, if you use stereo cameras or more than two, then with that you can get some range. Okay, yes, you know that the good thing about the stereo cameras or several cameras is you can use a stereo or multi-view structure from motion and you can get range. And again, if you want to know about stereo vision and disparity and depth map and so on, here is a video under my playlist Computer Vision where you can see how I explained it, and then I have given you a code in OpenCV. Okay, so you can learn more about finding range from a couple of cameras. But here we assume that we are doing monocular, a single camera SLAM, so the only information we have is alpha, the only thing we can measure. We also call this a bearing only SLAM. Okay, so with bearing only SLAM, how can you find all of the landmarks? Because the goal is to locate these landmarks. We don't need to just know at which angle we can see them, we have to know their distances. The way we do it is basically, as I said, similar to the problem of structure from motion in computer vision, and it's a multi-view one, right? So if you watch that video that I mentioned to you, structure from motion, the goal in that structure from motion is you don't know the scene, in this case the landmarks, and you only have a bunch of pictures of the scene, and the goal is not only to reconstruct the 3D scene but also estimate the position of the camera using which you took all of these pictures. And if you think about it, that's exactly the same as monocular SLAM. Because in this case, your camera is the same as the robot. It's rigidly attached to the robot. Now, it can have separate degrees of freedom, but the position of the camera is basically the position of the robot. So if you can estimate the scene and the position of the cameras from a bunch of pictures, that's exactly like estimating the robot position as it moved from this point to this point to this point along the path, and you can find the landmarks. So it's exactly the same as a structure from motion with multi-view, of course, because each view is taken on one of the waypoints on the path. Okay, now what's the difference here? Then if that's exactly the same, the idea is the same, but the formulation is not. In a structure from motion, we don't use any probabilities. Okay, we do not bring Q's and R's that we had in these equations. We don't consider randomness in our system. Okay, yes, we don't have those Q's and R's, measurement noise and the motion of the camera or the robot noise, which we call disturbance. Here we also include them, and we try to get a close to optimal solution. And of course, as you know, extended Kalman filter will not, like the standard Kalman filter, it's not going to give you the perfect optimal solution. It only gives you a close to optimal solution, not perfectly optimal. So the only difference is here we use a probabilistic framework. Okay? And of course, similar to structure from motion, we can use triangulation and several views to find the distance or the range information that we have lost because of using a single camera. In one of the formulations that is done, this video here, my goal is not to go over VSLAM completely, because VSLAM is a big topic of its own. So if I want to explain VSLAM, I need to spend 1 or 2 videos just to briefly go and explain the material. So the goal here is just to introduce you to the idea of VSLAM. I don't want to make it like perfect, and the animation and the video that I'm going to show you, not the video, the MATLAB code that I'm going to show you, which has animation, this is assuming we have a LiDAR, not a camera. Later on, I will make one with a camera via VSLAM, and I'll show you that later. So the goal here is just to introduce it to you. The only difference here is that extended vector here, okay? The extended vector is going to be what in this case? Still, you have some pose plus some landmarks. Well, you might say, well, that's the same thing as before. No, this time, this x of t, the pose, is not simply going to be x, y, and theta of the robot, because you have a camera attached to the robot, and the camera can move independently from the robot, okay? Unless it's rigidly completely attached, it can do pan, tilt, and so many other things. So here, your camera pose is going to have, in one of the common formulation, they considered 13 components for it instead of 3. And in this case, your scene is not 2D anymore, it's a 3D scene, because each point in the scene has X, Y, and Z, right? When you're looking with your camera, it's not like a 2D LiDAR. Each point has X, Y, Z, so these M's, they have 3 components in them, not 2. So for N landmarks, you have 3N components. Now, what is a landmark in monocular? We have to talk about it. But first, let's look at X. So what is X? The X that has 13 components has 4 vectors in it. R, Q, V, and omega. And these guys are all vectors. So R has X, Y, Z of your camera. Okay, now if the camera has a fixed Z, because it is attached to the robot, then yes, it could be X, Y, and a fixed number, and that number does not need to be updated, so it can drop down the position of this to 2. But that's not always the case. If the camera is attached to a drone, not to a mobile robot on the ground, then this R has X, Y, and Z. Okay? So, because many times when you do monocular SLAM, it's not necessarily always attached to a ground robot, it could be attached to a drone. So it can have 3 components in general. What is Q? Q shows the orientation of the camera. And again, it could be basically the orientation of the robot and or orientation of the robot plus the pan and tilt. So this is the orientation, and this is done with unit quaternions, okay? So we use unit quaternion, so this is like Q0, Q1, Q2, Q3. If you don't know what unit quaternion is, I recommend you watch my video on unit quaternions, okay? And I explain unit quaternions for you. So here, that Q has 4 components, then V and omega, the linear velocities of the camera and the angular velocity. So this is like omega x, omega y, and omega z, and this is like vx, vy, and vz. So using these, we should be able to basically completely identify the pose of the camera at any point. And these landmarks that, as I said, they have 3 components. What are they? They could be x, y, and z of these landmarks. And what kind of landmark are we talking about? Typically, the landmarks are interest points. What interest points? These are like SIFT features. They are like surf features or anything else that your system can keep track of in subsequent frames from different poses. So M's are the basically features of interest, robust features that you can track. Okay? If that's the case, then you might say, what is now my motion model? Well, in this extended vector y, if you remember, the only thing that changes over time is the pose. These landmarks, if you remember, they don't change. So all we need is these 13 components in the X, in this case, how are they changing over time? We have to come up with a motion model for that. What is that? So the position can clearly come from what? The position can come from basically and the velocities and everything can come from a constant acceleration model where V is basically A times delta T and omega is equal to alpha times delta T, assuming that, of course, you have to add this to the previous V. So if we have some unknown A and unknown alpha, which your system, by the way, has to find, and these are modeled with zero mean Gaussian distribution. So each one of them is like n of 0 and some number. You might call it, for instance, sigma of A, and this one is normal of 0 and sigma of alpha. Okay? These are unknown, and they are basically a part of your unknowns of the system to find. So if we use constant acceleration model between two frames, then your V is going to be added, as I said, to this A times delta T. So that is the same as V naught here. Okay, and this is like omega naught. So these are your change in V and omega, and then the quadratic form for change in the position and the change in the quaternion or the angles. And clearly you see this is a quadratic form, because if you replace this V by A delta T, you're going to get A delta T squared, okay? And you know, in a constant acceleration model, the position, whether linear or angular, they are both going to be quadratic, and that's exactly what it is. Okay? So, and as I said, your alphas are not going to change, or R's in this case, or it could be, instead of alpha and R, it could be, for instance, X of that M0, Y of the M0, and Z of that M0, or anything else. They are not going to change, but your pose is going to change. So this is a very, very brief extension from LiDAR SLAM to visual SLAM. Okay? Now, the last thing before we look at the simulation is, and here, you see, I mentioned that for you here, that the features are the interest points to form the innovation term. Now, one thing that I need to emphasize here, this is very important. When we calculate the innovation here, let's talk about it very fast. When we calculate this, what do we have? This Z is the position in a camera, right? So really, this is like U and V that you see from that landmark. But this X that has a landmark in it, when I observe it, that X itself, as I said, is some X, Y, and Z. I cannot subtract a 2D from a 3D. This is in world coordinate, this is in camera coordinates, or image plane coordinates. Correct? Let me see if I can write a little bit nicer. So how do you compare? How do you subtract? Of course, you have to take this world coordinates back into the image plane, and that is done inside this H function. You have to use camera extrinsic and intrinsic parameters to convert this world coordinate into first the camera coordinate, then the image plane coordinates, so you can subtract. Okay, so pay attention that your observation model has to have all of those. Now, finally, what are the major challenges in STEM? Even if we can form these big vectors and estimate them and everything and do a good job, what are the major challenges that are remaining in SLAM? One is the biggest assumption is violated. What was it? We assumed the system is static. Well, what if it's not? If you have a robot that is moving somewhere and the system is changing all the time, as I said, a Roomba is like a simple example, but the self-driving car is way more interesting example, right? The people, the cars in front of it are changing all the time. And there could be constructions and everything. So it has to do some form of dynamic SLAM SLAM in dynamic environment. And that is actually a very hard problem, because now these M's that you had and they were not changing, these guys, now they will change. And you have to come up with some way to kind of model these changes and determining that. That is very hard. The next one is sometimes you don't have one robot that does the SLAM, you have several robots, you have cooperative SLAM. Okay, how would you convey all of this information of these different robots together and use several robots to map the environment for you instead of one? And one of the hardest thing is incorrect data association. That is one of the hardest thing that you have, because guess what? If I want to show you, let's say this robot is navigating this environment and there is one landmark here, but there is one landmark right next to it or elsewhere that exactly looks the same or very similar. So if my robot is here, when it looks at this, and let's say it is using a camera and it finds what? It finds some basically surf features. If it see the same surf feature here, then instead of saying, hey, I found this that I have seen in the past, it might say, well, now I'm looking at this guy. Yes, if they are visually very similar, then sift or surf does not make much of a difference. You can easily mistake one for the other one. Or if there are environments like lines or something, so let's say there is one piece of line here, 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 here. So you broke your walls into a bunch of small lines. And if my robot is going like this and looking at these walls, okay, if two walls are very close to each other, two pieces of walls, right, two scans, or two landmarks here, two small pieces of line, as I said, you can easily mistake this top line here for this bottom one because the ranges and their angles are close. Okay, so if you see similar portions of the walls, then you can easily think that, hey, I have seen that before, and you can do wrong data association. And that is one of the hardest thing that is not easy to overcome. So now with all of that, let's go ahead and look at this code here. In this code, you see this is how I started my Q and R, the motion noise covariance and the measurement. Now, I assume that my motion noise is not too bad, so my encoders are good. The drift is not big, but I can change them to any number I want. My measurement noise is also not super bad, but I can always change that. My initial position inside the environment is this, X, Y, and theta, and my initial covariance for the pose is very small. As I said, I know them very well. How many landmarks do I have? I have 50 landmarks, and all of these landmarks are pieces of lines here. Okay? And then I have a bunch of motion sequences, and the way that I provided these motion sequences is a bunch of straight, kind of not straight, you'll see they are not perfect straight because of the noise, but they are moving along a line and then turning and then moving along the line and turning. So that's basically what these are. These are the U's that I know ahead of time. This is how I want to navigate the environment, and I designed them so that it can visit kind of most of the environment and give me a loop closure. And this is the total number of steps of simulation. The time between them is 0.01, and you can change all of that here. So then I start my loop. I also have another interesting thing in it that I added, and this is obstacle avoidance. So if my robot, when navigating the environment, because of one of those sequences is mixed with noise and it doesn't follow exactly that, and it's about to hit into one of the walls, one of the line segments, what it does, it will as long as the distance between the robot and one of the pieces of line is less than 0.4, it changes the command. And what are these commands here that you see? These commands are basically the U and the V and omega. So if I want to say that, these are U and V and delta T. Okay, these are the things that I'm commanding here. So the first one tells it to how much, V and omega. So this is the straight motion, the speed of it. This is how much I should turn, and this is for how many steps. Okay, or instead of delta T, let's say steps. For how many steps, which corresponds, of course, to how much time I need to do that motion. Okay, so this is the motion sequence that I have. Now, if the distance falls below this, what's going to happen? You'll see that, let me see if I can show you that. So it's somewhere in the code. I slow down and I turn. Okay, here. If the obstacle is detected, when the distance goes below safety distance, what I do, I bring my first component, which is V, to about 10% of it. So I slow down, and then I will change my U2 to some angle. So I change my omega to some angle. What angle? Negative pi over 20, negative 9 degrees. So instead of rotating counterclockwise, I rotate clockwise. Why? Because all of these motions, as you see them, all of the rotations, all of the second number, they are all counterclockwise rotations. So here, by going clockwise rotation, I move away from the wall. Okay? So keep that also in mind. So I do all of that, and then you see I read V and omega, and then I start putting them in U, and I pass my U. There are several utility functions. This U is passed to this utility function, which is called the motion model. So you give it the current pose and the U, and you get the first and the second component, V and omega, and based on that, you update your position. So this is basically your odometry model. Okay, here. Then, of course, at each point, you check for whether there is an basically collision or not. Then the other things you need to do is to perform the Kalman filter, the extended Kalman filter. And if you remember, it has a prediction stage and a correction stage. So these are these two functions. There is one for prediction and there is one for update or correction. So update is the same as correction, if you want. Okay, that's the same thing. And these functions are also down here. So this is the predicted one. This is the update or the corrected ones. Okay, so here we use the Kalman filter commands, and we'll update with the basically those formulas that I showed you for extended Kalman filter. We need some Jacobians here, of course, right? And these are the formulas for the Kalman filter gain and everything. So these are all provided here. Then there is, of course, the observation function. So you need to observe a line. Now, how would you do it? Here, from your position of the robot, you will measure the range and the bearing angle to where? To the midpoint of each line. As I said, each one of those landmarks that you see is a small line segment. So from my current robot position XY to the midpoint of these, this observe line function, which is my H function here, my observation model, this is going to give me some value R and some value alpha. Okay, so that's what it does. And one important parameter here is this guy, 4. So I can put some variable for this and say max detection range. This is your maximum detection range of your sensor. So let's say if I have a LiDAR or ultrasonic, here I assume it can only see up to 4 meters ahead, no more. Okay, and you can change that, and that is definitely going to change the results. Okay, and I also have two other utility functions for plotting. One, it plots the robot. The other one plots the uncertainty ellipse around the robot pose. And that takes the P matrix. It only gets the first two components of the P for X and Y, and then based on their eigenvalues, it scales the ellipse up bigger or smaller, right? And then plus the ellipse also rotated for you based on the eigenvectors of the covariance matrix. So this is the entire code basically here. Let's go ahead and run it. Of course, you know, the first time you run any code is slow, but definitely, there we go. So here, the red is the actual position, and the blue is the position calculated from SLAM. These black walls are the environment, and each one of them is made of so many smaller lines. So they are not one single line, they are several smaller pieces of line. And on the top, you see the step. And the other thing is, you see as the robot moves, look, this ellipse gets bigger or smaller. Now, the reason it gets smaller sometimes is that wrong data association, okay? But you see, typically, look here, okay? It thinks that it has seen this, but it probably is here. Now, sometimes the collision avoidance doesn't do a perfect job, okay? The slow down and turning does not do a perfect job, but here, and I run it several times for you, each time it's going to give you different results. Why? Because there is randomness here in the system, Q and R, remember that. So here is the environment. You see it's like two rooms, an inner room and outer room with some exits, some doors or windows. So the black is the actual map, and the reds are the midpoints of the estimated map. And you see that they are perfectly fitting. So if I connect these red circles to each other, my measured map is very, very close to the actual map. Now, of course, here I have small noise in the measurement and small noise in the model. If I increase them, that is going to ruin the results. I mean, not going to be as beautiful as it is, and I'm going to do that for you. The other thing, remember, my maximum detection of the sensor is 4 units. So basically, if I'm here at -6, it can see all the way to -2. Okay? So it can see basically from this wall to this wall all the way. Of course, it cannot see all the way to the other side. Okay? And so basically, this is a simple simulation. Let me run it one more time. I want to explain the change in the covariance matrix, and then we come back and change this Q and R, and we'll see what happens. So look at the size of the ellipse that gets bigger because of the odometry noise. You see? It's getting bigger and bigger. But when it goes inside, it thinks that it has seen something, and it's the wrong data association. It's actually the data outside that it has seen, but it kind of brings down the covariance a little bit temporarily because it thinks it has seen this environment. Okay? And you see it starts growing again. Now it is shrinking. And you see here, when it comes back to the beginning, you see it is very small compared to previous. And guess what? You get a relatively good map, right? The estimated midpoints and the true landmarks. Okay? And you see they are relatively close to each other. Now, all I need to do is to come back and say, well, guess what? I think there is some slip on one of the tires, okay, or both of the tires or anything. And because of that, guess what? My basically disturbance of the motion model is large, okay? Just that. So let's see what happens now. First of all, the V and omega commands that I gave are not going to be that beautiful because there is a lot of noise in the motion. So the path is going to be very random. Okay. And there we go. It got trapped and now it moved out of it. As I said, the obstacle avoidance here is by no means that perfect. Okay. And it just went outside. So it did not do a good job. And now look at that. Cool. Yeah, you see? And basically it cannot give you much data around here because it did not come here and it did not scan it. Okay, so if you make those big, you have to be careful. Your result could be dramatically changed because now you are not really following your commands, V and omega, and your robot can go somewhere that you didn't plan it to go. Because especially in this case, they are pre-planned. These motions are pre-planned. You see here, sometimes it just does some craziness and just passes the wall. So this code definitely needs some improvement and it's not perfect. I can make the speed to go just perfectly down and becomes very small. You see here it is doing something, but not always. So adding this noise to the motion can have bad consequences on the result because it does not follow the path that I intended for it. Instead, what you can do, you can add to the measurement noise. So make this like 0.1 and make this like 3 or something. Let the measurement have bigger noise. Okay, so at least the robot follows the waypoints that I intended for it. And the measurement noise to be more. So now you see the distance between the two paths is growing a little bit, of course, if it doesn't do craziness here, and it probably does. It comes, yeah, there we go. It went out. So as I said, one thing I can do is to go back in this collision avoidance, and you see here when it says go down to 0.1, maybe I do it to 0.01 or something, make it really almost stop. Okay, so it doesn't pass the walls and something. But you know, in many times in SLAMs, you can have real-time control over the motion of the robot. In this case, V's and omegas are pre-planned. So the only real-time effect that I have on them is to change them by some simple algorithm. And if you want, you can make it very more complicated. Okay, so feel free to change this. I did this as a starting point. It doesn't mean it's perfect. It's not. But since I did not find too many good data here and there, too many good code, there we go. That's what I did. And now if you look at this map, if you connect these line points, you see that now if I connect them together, clearly the wall that I have is not going to be the same as the black wall because I have some measurement noise. And look at this. This is also going to be tilted. This is going to be tilted. This is going to be tilted. So here you clearly, right, if I just go ahead and insert a line here, you clearly see this is going to be the wall that I expect there. And similarly in other places, you see that my expected walls are a little bit tilted because I have measurement noise. Okay, so feel free to play with this, learn from this. I'm going to give you a download link under video description. Hopefully you learn basics about SLAM, especially the LiDAR SLAM, but hopefully in one of the future videos I can talk more about visual SLAM and make a demo like this. So thank you so much, and I'll see you in the next lecture.